The most effective way to prove fundamental identities is to leverage the inherent symmetries of the mathematical structures involved. By recognizing that certain symbols are totally antisymmetric, meaning they flip their sign whenever two of their indicators are swapped and vanish entirely if indicators are repeated, researchers can avoid performing explicit sums for every possible combination. This approach dictates that if two different expressions share the exact same symmetry properties, they are structurally identical. To confirm the proof, one needs only to verify a single non-zero case. If the values match there, the established anti-symmetry guarantees they will match across all other valid combinations. Moving beyond simple visualizations, the mechanics of index notation allow for the representation of complex rotations as a series of labeled components. A critical part of this mechanical process is the use of indicators that act as filters, often referred to as delta contraction. These indicators effectively collapse a complex sum by forcing specific labels to be equal to one another. This transformation is what allows a nested series of rotations, which are difficult to track manually, to be distilled into a simple difference between two scaled vectors. The result of a nested cross product has a very specific geometrical destination. When you take the cross product of two vectors, the result is a third vector perpendicular to the plane they form. Crossing a new vector into that result essentially rotates the final vector back into the original plane. Because the final result must lie entirely within the plane defined by the two inner vectors, it can be viewed as a vector sum of those two original components. This provides a powerful visual check. The final vector is always pushed or pulled along the lines of the two vectors that define the plane, with its final direction and length determined by how the third vector projects onto them. The practical value of these identities lies in their computational efficiency. A manual approach to nested rotations is cumbersome, often requiring roughly 30 separate operations. In contrast, using the established identity, often called the BAC-CAB rule, reduces this to between 7 and 15 operations by focusing on simple projections. This efficiency is amplified when vectors are orthogonal, perpendicular, as entire sections of the equation vanish instantly when their projection becomes zero. In the realm of advanced physics, such as electrodynamics and fluid dynamics, this efficiency is a lifesaver. It is used to simplify the wave equation by converting a difficult curl of a curl into a much more manageable combination of gradients and Laplacians. By turning messy, nested rotations into straightforward dot products and scaling, physicists can solve complex field equations that would otherwise be computationally overwhelming.